Hi everybody, I would like to welcome you to our Parent Math Night. My name is Burdess and I'm a math teacher. I wasn't always going to be a math teacher. It wasn't until I had a university professor who showed us that math could be understood instead of just performed that I realized I could help my future students to do the same. Fast forward 11 years and here I am. I just finished my master's degree in math education from Simon Fraser University. I was lucky enough to spend the last 2 years learning more about how kids learn math and how to develop a deep understanding, and more importantly, a confidence, using and working with numbers and mathematics. I'm normally a junior high teacher, but I've also taught grade 4 math just to see what it's all about. I have 2 young children who are just starting to learn about numbers, so we have fun with math at home. Please don't sit back and relax. Please engage, take risks, and learn. Please pretend that you are a student and enjoy the presentation. So I love math. More importantly, I love teaching math. I love when kids get it. It's a great feeling. I'm hoping I can share that with you today. I want to show you what it is your children might be experiencing in math class and how you can help. Subitizing is learning to identify numbers without counting, recognizing numbers at a glance, and it is crucial to the development of number sense and basic fact acquisition. Young children need to learn to trust the count. One of the most important skills for students, especially at a young age, is the skill of subitizing. Subitizing is the ability to recognize at a glance what the number is. So we want students to be able to look at this card and realize, for example, very quickly that this is 1. Very quickly that this is a 10. This is a 5. Now we can help our children learn to subitize by talking about numbers in the world. Whenever they see numbers, for example, when you're driving in the vehicle and you see a stoplight, it's arranged in 3. We can talk about, how many lights are there. We can talk about how many dots are on dice. We can talk about how many numbers are on playing cards. Fingers are very, very good for subitizing because every kid knows at some point that this is 10. This one's 5, this one's 3, this one's 2. They're very common ways to represent number, and we really want children to come to understand and to really be able to see those numbers. I'm going to show you some math activities for teaching number sense. You can do these activities using dice or playing cards. I'm going to show you using my base 10 frames. They're also very easy to make if you'd like to make your own. Remember that subitizing is learning to identify numbers without counting. We want them to be able to recognize at a glance what the number is. This is very crucial to the development of number sense and for basic fact acquisition. Young children need to learn how to trust the count. So the first game is just to be able to subitize. So whether you're using playing cards or dice or fingers, students should be able to quickly recognize that's a 5, that's a 2, what's that one? And that one, and that one. So once your child has become comfortable with subitizing and used many different ways and different objects to help them practice, then we can do the addition game. So we can show them 2 amounts. And they can add. 6 plus 5 is 11. 1 and 2 is how many? It's 3. You could even have them take an empty 10-frame card and add them together to show that it's 3. There's 8, and there's a 4. Oh boy, that's bigger than 10. What does that look like? Here's the double game. I want to know what the double of that number is. So the students can visualize double of 4, and they can double it and realize that it's 8. What's the double of this one? It's 12. What's the double of this one? 6. Double of that one. Fill the frame. It's 10. Now remember to try these games as your children are developmentally ready for them. Some might be too difficult, so then just scale it down and make it easier. Some might be too easy, so then you can push them and you can make it a little bit tougher. The next game is more or less. So one person turns this card over, One person turns this card over and you ask the question, is it more or is it less? So this person would say mine is more because it's 8. This person would say mine is more or less because it's 7. More or less. You can even ask, what's the difference? Oh, this one is 7 and this one is 1. The difference is 6. More or less. Mine is more. No, mine is less because you have one more colored in. Last game I'm going to show you is just concentration. So what you could do is you could spread out all the cards. Remember, you could use playing cards for this as well if you wanted to. And they have to match up to make 10 pairs. So they would flip over 2 of them, just like the normal concentration game, and they would say, okay, this is 5, this is 4, oh, that's 9, that doesn't make 10. Turn them back over. The next person would go, oh, that is 8, that is 9. Nope, that doesn't make 10. 3 and 7, that makes 10. So I would get to keep this one. So these are some games that you should try along at home with your children, and just remember to have fun with it. Don't make it too competitive and don't make it much of a race. Just make sure that they're just getting used to working with these numbers.
Number sense is an intuition about numbers. Number sense can be developed by providing rich mathematical tasks that allow students to make connections to their own experiences and their previous learning. Mastery of number facts occurs when students understand and recall facts, and is expected to be attained by students as they develop their number sense.
Good morning, John. Today I'm going to talk about numbers. Numbers are great because we can't really understand the world. It's too big. There is, for example, no way for me to really understand what a million of something is. 2, I got 2. 2 is just one thing twice. But 2 million? How? As an example, I know how long a second is, and I know how many a million is. It's just 1,000 thousands. And 1,000 is just 10 hundreds. I can say those words, and so then I should be able to know how long it was a million seconds ago. But I can't. I have no idea. It could be a week ago, it could be a month ago, it could be a year ago. In fact, let's do a scientific experiment right now. Everybody write in the comment box, no math allowed, no Google searches, how long ago you think it was a million seconds ago. Like how many days or months or years you think it was. Now I'm going to look it up and I'm going to tell you the answer. It was the Monday before last, a million seconds ago. Interestingly, a billion, also a big number. A billion seconds ago, it was not like last month, it was not last year, it was 1982. So by going from million to billion, we went from the Monday before last to like Michael Jackson's Thriller and E.T. and the Falklands War. A billion to a trillion seconds ago, we're going from 1982 to 31,000 years ago when humans were first being introduced to Europe. Hello, it is nice to meet you, Europe. I don't know who was doing the introductions. Also, that probably they didn't speak English. And it goes the other way too, like small, tiny, super tiny, small amounts of time, like a nanosecond. You've heard of a nanosecond. But how? It's the amount of time it takes for light to travel a foot. Remember a billion seconds ago was 1982, a billion nanoseconds ago was by definition 1 second ago. And yet, check this out, the fastest computer in the world can do 17 million calculations in 1 nanosecond. I'm not gonna get my mind around that! It's amazing to me because nobody really internalizes that information, but it allows humanity to control the world and to do so many amazing and cool things. For example, all that math allowed us to put the Kepler Space Telescope in orbit, where it told us that there are between 15 and 30 billion Earth-like planets in our one galaxy, and there are more than 100 billion galaxies in the observable universe, and the observable universe is who knows how big of a fraction of the actual universe, which may in fact be infinite. No edge! Giving us yet more incomprehensible data about how amazing our universe is. We're not designed to understand that stuff, but we are designed to want to understand it, which I may be wrong that that is the most wonderful quality of human.
I just want to show you one of the ways that your children may be learning about math. And this really helps them develop their number sense and their place value. So instead of seeing a number that's just 216, 216, we want children to realize that this number is actually 200, 10, and 6. We want them to be able to take the number apart and build it back together so that they really start to understand that 216 is 16 more than 200, for example. Another example could be 975. So instead of the students focusing that it's just 975, we want them to be able to decompose the number into 900 plus 70 and 5. When students can see this visually, they really begin to develop a better understanding of number sense and place value. Once students have a good understanding of place value and once they have a good number sense, they'll be able to see an easier way to add 216 and 975. They may break down their hundreds, their tens, and their ones. And we can do the same for the 975, 900, 70, and 5. And then they can add the different parts together. So it can add their 200s, their 200 and their 900, their 1100, their 10 and their 70, their 80, and their 6 and their 5, or 11. And now it's all about adding the numbers together. So we can go 1100 plus 80 would be 1180 plus 11, 1191. Now, students may choose to do this differently. If 900 is too big of a chunk, they may break it up into 500 and 400 and then add 200. If they'd rather use 50 and 20 for 70, they can do that. Students start to become very flexible and fluent with numbers, and they are beginning to develop a better understanding. I'm going to show you how to play Salou. It's a game that can help your children to develop number sense and get them working with numbers and operations. So for this first game, what we're going to do is we're going to take out all of the face cards from a deck of cards, just because then the numbers are smaller. If you'd like to extend the activity, you can assign numerical values to the cards, for older children. So what's going to happen is my two players are going to take their top card, but they don't want to see their own card. They can show the other person their card, and they can show me. So I'm going to look at both of those cards, and I'm going to say, so I'm the third person in the group, I'm going to say the sum of your cards is 16. They're going to take their time, they're going to look at the other person's card and decide what the value of their card is.
I think my card's a 9.
I believe mine to be a 7.
Good job. So now we'll do the next. The sum of your two cards is 10.
I believe my card's an 8.
I think mine is a 2.
Good work. We'll do one more. The sum of your two cards is 15.
I believe my card's a 9.
I believe my card is an 8.
Okay, can you help Mike with his card?
You're close, Mike. Try again.
What did you say the sum was?
The sum is 15.
I believe
you've
my
ever played crib.
card is a 7.
That's correct.
Other variations to this game may be to find the product of the cards. So they'll both flip up their card, and I will look at them, and I'll say the product of your two cards is 35.
Well, my card must be in 5.
Mine must be a 7.
Good. Now let's do another one. This time I'm going to tell them the difference. Now difference can be fun and tricky. So let's see. The difference is a 0.
I think I have a 4.
And I think we have the same card, which would
Excellent.
equal 0.
Bazinga!
Let's do another one.
Ready?
The difference is a 5.
I think I have a 5.
I must have a 10.
Okay, let's do one more. The difference is a 9.
I must have an ace.
I must have a 10.
Excellent. Now, with differences, for example, if one of the players had a 6 and one of the players had a 3, I would say the difference is 3, but those aren't the only combinations. The other person could actually have a 9. So
Right.
that's where some discussion can come into play.
Yeah.
So, like, if I'm...
I got it. We don't have to do a race with you two. So when it's Maddie's turn, she's going to do product. Your turn, addition. Perfect.
Okay, and if you don't get it right the first time, you don't get the point.
Okay.
And that means I can keep score. No.
Let Grandma keep score so you can concentrate on what you're doing.
Hey, wait, but I'm just going to show her something.
I know, I just
After
put a
you get
tick.
4 points, you
Put a
put a
line
tick,
through it.
and that's... She knows how to keep score.
Okay, slide that way a little bit.
You're teaching her like she's a child.
Okay,
I know how to
we'll
keep
start
it.
youngest first, so Shay will go first, so this is going to be addition. Okay?
And do you have a certain time to get that?
16, don't worry about it. 16.
7.
Yes!
So Shay,
Go Shayla! Okay, you guys ready? 100.
10.
Yes, Matea.
Oh.
28. Or you're doing addition, right?
yeah.
So Shay 11.
3. No, 4.
It's okay, go again, just think.
Four.
Don't try and rush. 11.
4. I have 4.
You have 4. Good. You nailed
Okay,
it.
but I don't get the point because...
I'd like for you to take a few minutes and think about the 2 questions above. What did you enjoy about math in school? And what did you not enjoy? When I ask these 2 questions to parents, I get a variety of answers. Some people enjoyed math. Some people were good at it and they were fast and they were able to regurgitate the work that teachers showed them on the board. They liked the practice questions because they knew what to do and it made them feel good because they could easily find the answers. A lot of people talk about the anxiety that they felt when they were learning mathematics. They felt pressure. They felt that they had to come up with an answer quickly and often on the spot in front of other people. A lot of people told me that they were never good at math and that they shut down at a very early age. A lot of people told me of their feelings of anxiety even as an adult and how they just say, "Oh, I'm not good at math. I don't go there." What do we want for our kids? There are 2 important concepts to think about and understand. The first one is that speed is not important. It doesn't matter how fast kids can come up with answers if they don't understand where they came from or why they work. We want to give kids time to think about what they are doing and think about numbers as they're solving problems. The second thing is that memorization is not always indicative of real learning and deep understanding. We need to teach kids who can easily memorize to think more deeply and explain their thinking. We need to help kids who have difficulty memorizing develop their number sense, see patterns, and make connections so that they can deepen their understanding and become more confident with their math skills. What I really want for my kids is for them to be able to have confidence while they're learning math and all other subjects. I want them to be able to persevere, to take risks, to solve problems. I want them to be able to collaborate, communicate, work with other people. And I really want them to enjoy learning. What do the experts tell us? John Vandewall says that the standard algorithms, when introduced too early and without number sense, can cause difficulty for many students. He says that most, if not all, mathematical concepts and procedures can best be taught through problem solving. This is why our children are learning math differently than how we learned math. We know more about the brain from the last 10 to 15 years of brain research than we did in all of history.
This is my favorite example of working students through number sense and reasoning. This is a junior high example, although it's not limited to junior high in any way. We're supposed to fill out this table by only using mental math. Now, percent is so important in our everyday life. We use percentages to calculate tax, to calculate tip, to calculate interest on our credit cards or on our mortgage. We also use percent when we talk about investments. Now, percent traditionally is taught with a variety of methods. Most involve little to no understanding of the mathematical concepts. For example, we would set up a cross multiplication and we would cross multiply and divide, or we would divide by 100, move the decimal, and then multiply, and very, very confusing for students. This way is a way that will work for any single percent, and it can all be done with mental math. If we look here, we are given $80 to start, and this is equal to 100%. So what we would ask is we'd ask that the child thinks about, or adult in this case, thinks about for 50%. Okay, so I think half of 80 is $40. Now I can go wherever I want to next. In fact, I'm going to go right to 10% because I know that 80 divided by 10 will give me 10%, so I know that it will be 8. From my 10%, I'm going to go to my 1%. And I know that 1% is just divided by 100 because that would be 100th, so it will be 80 cents. If I double that, that will give me 2%, which is $1.60. If I half my 10%, it will give me 5%, so 4. Let's see, if I times my 4 by 5, it will take me right to 25%, so this will be 20. Now with my benchmarking table that is complete, oh look, I can check and make sure if it's right here. Okay, good. Now I can calculate in my mind the percent of any number. So I'm going to try 30% of 80. For 30% of $80, I'm going to use my 25%, which is 20, plus my 5%, which is 4. So I know that 30% of 80 is 24. There's also other ways to figure it out. I could use my 5%, which is 4, and I can multiply it by 6. 4 times 6 is 24. Let's try another one. Let's try 75% of 80. 75% of 80 should be fairly easy. My 25% of 80 is 20, and if I just multiply that by 3, I will get 60. Okay, let's try 90% of 80. So I'm actually going to go 100% of 80, which is $80, and I want 10% less, minus 8. So 80 minus 8 will be $72.
Whenever possible, I would practice percents with my children in a mental math situation in real life. So while we're at a restaurant, when we would get the bill, I would ask them to take their time and to mentally calculate, for example, the tax on the total bill. And then I would also ask them to mentally calculate the tip. So for example, if the bill came up to be $80, we would be able to work through in our mind what 10% would be. And if I wanted to leave a 20% tip, I could double it. And if I wanted to calculate 5% tax, I could half it. We add it all together, and there we go. It's a great opportunity for us to see why it's so important to, first of all, be able to understand percentages and also to be able to use them in everyday life.
I figure 75% to you, Pon Ma, and 25% divided between the 5 of us. Yida, Crowbar, myself, Tom, and the baby. That makes 5% for each one of us.
Billy, you're cheating yourself. If there's 25% divided among the 5 of you, that's 14% apiece.
Oh, no, listen, Pa. I wouldn't cheat you. You know I wouldn't. Now, look here. I'll show you. Let me rub this out here. And now, 25 divided by 5 is 5. You see, 5 won't go into 2, will it? No. But 5 goes into 25 5 times, you see?
No, you're wrong, Billy. Now, I'm a pretty good mathematician. Now, 5 into 25, 5 won't go into 2, will it?
No.
But 5 goes into 5 once. Now, we didn't use the 2 before, so we bring it down here. Now, 5 into 20 goes 4 times. There you are. 5 into 25, 14.
No, look, Pa. Let me prove it to you now by multiplication. 5 times 5. 5 times 5 is 25.
Really, I'm surprised you're learning.
Huh?
I'm surprised that you're learning. Now I'll show you. 5 times 14 is 25. 5 times 4 is 20. 5 times 1 is 5. 25. That's it.
No, look, Ma. Look, you're wrong there because I'll prove it to you. We'll put down 5 14s here. 14. There. Now I'll prove to you by addition that 5 14s is not 25. 4, 8, 12, 16, 20.
21, 22, 23, 24, 25. There you are. Better brush up, Billy. I don't want to see you boys cheated.
Grayson Wheatley says that a curriculum that emphasizes computational methods at the expense of mathematical concepts and relationships is no longer acceptable. He also says, gone are the days when the teacher explains meaningless rules from the textbook and students only practice computational methods. Kids can often just get by memorizing until junior high. That's when we see it fall apart, as they realize that they don't really understand. Sometimes this continues until high school. I was able to make it up onto Math 30 AP, and then I had a meltdown and had to drop out and retake some of my high school math. I realized that I didn't really have an understanding of what I was doing, and I wasn't just getting by memorizing anymore.
I knew that I took 40 plus 30. That equaled 70. Then I took 8 plus 2. And I knew that equaled 10. So then that equaled 70 plus 10 equals 80. Sucker. All I did was I added 40 plus 30 together in my head, and then I added 8 plus 2 together, and I put together the number 80, and that's what it equaled.
Go.
I added 3,000 plus 2,000 and got 5,000. And then I added 200 plus 600 equals 800. And then I added 90 plus 40, and it equaled 130. And then I added 4 plus 1, and it equaled 5.
Then what'd you do?
Then it equals, altogether it equals 5,935.
Go.
Okay, I did the tower method. I added 3,000 plus 2,000, which equals 5,000. And then I added 200 plus 600, which equaled 800. And I added 90 and 40 and got 30. No. I got 30. Wait. And I added 1 and 4 and got 5. And I added it all together and got 5,935.
Yes, I got it right.
Well, I know what 3,000 and 2,000 is, so I write it down. And I also know what 200 and 600 is, so I write that down too. And I know what 90 and 40 is, so I write that down too. And I know what 1 and 4 is, so I write that down. And then I add the plus signs. And then I'll add these two like this. And then there's my answer. And then I add these two to get 135. And then I add them and get my answer. And it is dead. First I minus 1 and it equals 108, and then I minus 10, which equaled 98.
Good job. Go.
I did the number line. I did 146, and then I added 4, then it got me to 150. Then I added 50, then it got me to 200. Then I added 10, which got me to 210. Then I added 3, got me to 3. And it got me to 213. And I added this up, and then it equaled 67.
I'm doing 356 times 2. 300 times 2 is 600, which I know 300 times 2 equals 600. I know 50 times 2 equals 100. And I know 6 times 2 equals 12. Now I will put all these numbers together and I will get 712. The question I'm going to show you today is 232 times 5. The thing I'm going to help me to use to find out my answer today is called matrix. So first I put my multiplication sign. Then I break up all the numbers. So I would put 200, and then 30, and then 2. So now I know that 2 times 5 equals 10. So now I know that 200 times 5 equals 10,000. 1000. So, and then I know that 3 times 5 equals 15. So I know add that 0 on, it equals 150. And I know that 5 times 2 equals 10. So now I have to answer all of these answers up. So I'm going to add 10,000, 1,000 together. And then I'm going to add 50, and then I'm going to add 150, and then I'm going to add 10. And I know all that together equals 1,160.
Oh. 57 times 3.
What are you doing, Carly?
I'm drawing a box.
Why?
So I'm breaking up the numbers. So 5 times 3 has to be 15, then 50 times 3 has to be 150. And 7 times 3 is 21. Now all I gotta do is add up the numbers. So there's no other hundreds, and then 5 plus 2 is 70, and then just 1. So the answer is 171.
Go ahead. For 62 times 4, I'd do 4 times 60 first, which would be 240. Then I'd do 2 times 4, which will be 8, and then you add them all together. And then that'd be 248. So for 39 times 6, if it would be too hard for you, I would go 40 times 6. But if you add them up, that would equal to 240. And to minus 6, because I added too much. So you have to minus 6. And that would be 240 minus 6. And that would be 234.
This is my question, and I have my 8 boxes here. Okay, I'm gonna go I'm gonna try to go 5, 10, 15, 20, 25, 30, 35, 40. And oh, look it. It's a 9. See, there's a 9 right there. And we have 40. Got 40. All those adding up to equals 40. So and we have 8 groups, so that means there's going to be 1 remainder. And there's 6 in each group. One, 2, 3, 4, 5, 6.
Why did you draw 6 circles, Haley?
Because if I have 67 things and I want to divide it by 6, I put 6 groups.
6 groups.
So I'm going to start with 10 because it's an even number, because 10 times 6 is 60. 10, 20, 30, 40, 50, 60.
So you put 10 things into each group?
Yes.
Okay.
And now I'm going to put ones in. 61, 62, 63, 64, 65, 66. So if I have 66 things and I want to put one more in, I can't do that because there's not enough. So your answer would be 11, because 10 plus 1 is 11. Then you have a remainder of 1, and that would equal 67.
Awesome.
$37 divided by 6 equals 6 times 6 equals 36. So 37 divided by 6 is to equal 6 with a remainder of 1.
Divide by 6. First, I'm going to put 10 in each screw. So I'm going to write the 10 right here. And then I'm going to put, and I used up 60. So I have to minus that. And that equals 17. And then I'm going to put 2 in each screw. So I'm going to put the 2 over here. And that uses up 12. So the answer is 5. And so I have 12, so it would be 77 divided by 6 equals 12 with the remainder 5.
So how do our kids learn multiplication facts, if it's not always just about memorization? One of the most powerful strategies is the array. By building an array, which is really just a rectangle, out of square tiles, for example, Dr. James Tanton, an international mathematician and math educator, can teach all the way up to grade 12 integers, fractions, polynomials, and algebra. We will start with multiplication, which connects naturally to division and leads into shape and space, and geometry. When you look at the rectangle or the array above, what numbers do you see? What multiplication do you see? Can you see a division?
So how are we teaching multiplication basic facts? One of the best ways is by building arrays. So for example, I want to build an array out of 24 square tiles, and I would ask the students to please build me a rectangle out of 24 tiles. This is one of the most common ways they will build it. This is a 4 by 6. So here we have a length of 4, and here we have a width of 6. Now we can clearly see that 4 groups of 6 is equal to 24. We can also see how 6 groups of 4 is equal to 24. Looking at this array, students start to take it apart. Now we can see 4 groups of 3 or 3 groups of 4, which is half of 24. Now we have double that, so we know that 2 groups of 12 is 24. Students could build this rectangle differently. They could build it as 2 groups of 12. This was smushed all together. Then we have an array. It's also a rectangle that shows 2 groups of 12. It also shows 12 groups of 2. When we think of the number 24, we could also build it as a rectangle that measures 3 by 8 or 8 by 3. Inside of the rectangle, students can break the numbers apart and they can see different groups within groups. The more students are able to do this, the more they see number and the more they'll be able to be fluent and flexible with number.
Almost 1/3 of Americans would rather clean their bathrooms than do a math problem. When Raytheon Corporation asked 1,000 middle schoolers if they'd rather eat broccoli or do a math problem, the majority answered, eat broccoli. Our students need to feel a passion for mathematics, and we want them to feel that they are capable and competent in this field. Math isn't something that we do to kids, it's something that they do. As teachers, we need to guide the learning, we need to encourage collaboration, we need to engage our students, make math meaningful and fun, help them appreciate mathematics and see the beauty in numbers and patterns in the world. This is also our responsibility as parents. How can a parent help? Encourage your children by using positive statements about learning and doing mathematics. Talk about math as being fun and interesting, even if you don't think it is. Allow your children time to reflect on the decisions that they make while completing a problem or working out a math question. Ask your children to help you learn what they are learning. Ask them to explain what they are doing. Ask the teacher for help if needed. Although you and your children may not complete a problem in the same way, Both methods may be valid mathematical solutions, and this should be an opportunity for inquiry and discussion rather than discord. Understand that mathematics is not about speed and that memorization doesn't actually necessarily equal learning. Please try to practice mathematics in real-life situations whenever possible. Don't forget to look at numbers in the world around us. Don't forget to practice when we're out at a restaurant and we want to calculate tip and tax. What about calculating a sale price at the grocery store or shopping at Ernie's? Let's try to make mathematics fun and interesting for our children whenever possible.
Why does my child not know the basic facts? Aren't they important? They are absolutely important. However, rather than relying only on memorization, basic facts should be learned by making connections, seeing relationships between numbers, building and decomposing numbers, and linking multiplication and division, as well as addition and subtraction. Our students must be able to reason and use number sense in order to use their math facts to solve problems and to be confident math learners. To memorize without understanding can actually be detrimental to the learning process, especially as higher level math concepts are introduced. Children who possess an understanding of mathematical relationships will be able to work flexibly and fluently with numbers throughout their lives. Students learn to read at their own pace. They should also be given the opportunity to understand mathematical concepts at their own pace. Allow them time, and remember that speed does not necessarily equal understanding. Does my child need to know all of the mathematical strategies? No. Your child needs to be able to show understanding of the mathematical concepts with a strategy that works for him or her. As a student's understanding develops, the strategies will become more efficient. Students are exposed to different strategies to allow them to connect to those that respond best to their needs as a mathematical learner. Why can't I show my child the traditional algorithms for operation? You can. This is a great way to discuss mathematics and to explain another strategy. Please note that using the traditional algorithm is not the only method that works, and is not always the most efficient way to solve a problem. Be sure to get your child to explain his or her strategy so you can discuss why both methods are effective. However, it is important that students practice what they learn at school. If they are unable to complete their homework, please speak with the teacher before panicking and trying to intervene.
Here are some helpful links for parents. If you go on YouTube and search "Why is Math Different Now?" by Raj Shah, you'll see a great explanation of the differences that we are seeing in our classrooms with our children. You can also search on YouTube, "What is the Common Core and what is it really trying to do?" Now, this is American, but Dr. James Tanton is an international researcher, educator, and mathematician, and he has been working with our teachers in our district. This is a great explanation of what Alberta has done, except that it was 8 years ago when we started. And finally, the last website, Talking Math with Your Kids, is a website full of resources and age-appropriate ways that you can talk about math with your kids at home.